One of the most important uses for matrix calculus is the estimation of probability density function parameters in multivariate distributions, or what is called the maximum likelihood estimation. If you are not familiar with probability density function or the maximum likelihood estimation, then don't worry. You can just deal with what I am doing in a purely mathematical way. However, I'll just give a very quick review of the concept and mathematics of the maximum likelihood estimation. Here is the main idea. Suppose you have some data points. For example, I can have here the marks of some students in some exam, for example, and the exam marks range from, let's say, 0 up to 200 marks. And now suppose you have those samples of student marks. For example, you have here the 200 sign and here you have the 0 sign, and let's say that here you have the 100 marks, and suppose you have this sample of student marks. For example, you have many students having marks in this position, maybe a less number of students near the 200 sign, and maybe a less also number of students right here, and maybe much more students here. So in this moderate or average range, you have a larger number of students. Now you want to describe those marks using some probability density function. For example, you might assume that those marks follow some sort of a Gaussian distribution, so maybe something like that. This here is the probability density function, and this says that there is a higher chance of finding a student with a mark in this region. So here we have a high probability for having student marks maybe in this region because this function has a higher value in this region, while for example in this region and in this region the probability is very low. So here you chose a Gaussian probability density function. You might also want to choose, for example, some triangular probability density function just like that, or maybe some other uniform probability density function, maybe like that, or whatever, depending on your understanding of your actual problem. For example, in the case of student marks, it might be better to use a Gaussian distribution or even maybe this triangular distribution, but using a uniform distribution is unlikely to be the correct representation, as for example the number of students that will get 0 marks is not equal to the number of students that will get, let's say, 150 marks. So using a uniform might not be the best option. Of course, the area under every one of those probability density function must be exactly equal to 1. So if you integrate any of those functions over the whole range of x values, you must get exactly 1. This is from the properties of probability. Anyway, the first step for your estimation would be to choose the general form for your probability density function. So let's say a Gaussian. Then after that you need to decide on the parameters of this Gaussian. For example, let's go again here to this same example, and suppose we have chosen to use a Gaussian distribution. Now we need to decide on the parameters of this Gaussian distribution. A Gaussian distribution in general in the 1D case has two main parameters. The first parameter is the mean of the Gaussian distribution, so the point right here, which is called the mean or the mu of the Gaussian distribution, and the second parameter is the standard deviation of the Gaussian distribution. So for example, you might choose a Gaussian distribution like that to describe your data, or you might use something like that having this mean, or you might have something like that. So this one and this one have the same mean but different standard deviations. And note that this right here is taller than this because I want to keep the area under both of them to be exactly equal to 1. So this has a less width, and so it must have more height. Anyway, we want to estimate those parameters, the mu and the sigma, and we want to estimate those parameters mathematically from our data points. So let's figure out a way to do this. Suppose we have the same example again, and we want to decide whether this Gaussian distribution is better, or for example, this Gaussian distribution. Clearly, visually, you can decide that this is really a much better representation for your data points than this right here. Now, we want to formalize this mathematically. Okay, let's call any one of those points Qi. Now, we say that the probability of the point Qi to exist given some specific mu and some specific sigma is equal to some number R. Now we know that those points right here did actually exist, and so the probability of their existence must be high. So we need to choose parameters mu and sigma that will make the probabilities of those points right here to be as high as possible, because those points did actually and really exist. For example, you visually prefer this Gaussian distribution right here because it has a high value for the probability density function in this region. So this Gaussian tells you that the probability for students to get marks in this region to be high, while this other Gaussian curve right here tells you that the probability of students to get marks inside this region to be very, very low, which is not true. So we want to choose our parameters that will make this probability for any point Qi to be as high as possible, since those points did really exist. Now, if the probability of any point of those to exist is high, then the product of all of those probabilities must be as high as possible. So here we define something called the likelihood function. So the function L of all our examples Q1, Q2 up to Qn, given all our parameters, which in general will be, let's say, theta 1, theta 2, theta 3 up to theta m in general, this is equal to the product from I equal to 1 up to I equal to n of the probability of Qi given the same parameters, theta 1 up to theta m. Of course, in the specific case of Gaussian distributions in 1D, then this will be simplified to the likelihood of all our data points again, so from Q1 to Qn, given only mu and sigma is equal to the product from I equals 1 to I equals n of the probabilities of Qi given mu and theta. Now I want this product right here to be as large as possible, and so I need to maximize this product, which means I need to maximize this function. So to maximize this function, I need to differentiate this function with respect to my parameters here and then equate to 0, and this will give me the maximum likelihood estimation of my parameters mu and sigma. Now suppose we have, let's say, 1 million data points. So now this function right here will be a product of 1 million terms, and every one of those terms is a function of mu and sigma. And so if you want to differentiate this, you will need to apply the product rule many times, and it will become very tedious and time consuming. So instead of that, we decide to take the log or the len of both sides. So we define another function L to be equal to len of the original function L, just like that. And so this will be equal to len of this product from 1 up to n of all my probabilities Qi given mu and theta, just like that. Now we know that len of AB is equal to len A plus len B. Now this means that this L, this capital L of my data points Q1 up to Qn given my parameters theta 1 up to theta m will be equal to the summation of len of probability of Qi given my parameters theta 1 up to theta m, just like that. So I transform this product into a summation, which is much easier to calculate the derivatives of than this product, so from I up to n again. Now I want you to note that the values for, let's say, mu and sigma that will maximize this small l function will be the same parameters that will maximize this l function, this len of l function, because the len will be something like that. That is the graph of len. So this is x, this is len of x. So if some value of the parameters will make x to be the maximum possible value, so x max maybe, then the same values for the parameters will make also len x the maximum possible value for len x. So this is len x all maximum. Very well, now one final note would be that for many probability density functions, this probability function right here will include some exponential, and we know that len of e power, let's say x plus y, is really equal to x plus y, and so this will simplify even more for many types of probability density functions. So this is called the maximum likelihood estimation. And in the next video, we will start evaluating some concrete examples, first in the 1D case and then for higher dimensions, and that's where we will need matrix calculus.